Hello everyone, my name is Javier Nieto. I conducted my research at INTA and I will present the progress of my thesis, which is focused on multi-fidelity models applied to aerodynamics. This research is co-supervised by Esther Andres at INTA and Rodrigo Castellanos at the university. Let's start by defining multi-fidelity in the context of aerodynamics. In this context, fidelity refers to how well a model or dataset approximates a real physics phenomena. As you know, in aeronautics, we have different methods to calculate aerodynamic properties. We can start with simple method based on potential flow. Then we have more complex TFD simulations, such RANS or LES, which provide higher accuracy. And finally, we can obtain fidelity data from wind tunnel testing or flight test. However, as fidelity increases, the cost of acquiring the data grows a lot. The core idea of multi-fidelity model is to exploit the strength of different fidelity levels, combining the abundance of low fidelity data with the accuracy of high fidelity data. During the literature review, I identified two main scenarios in multi-fidelity research in aerodynamics. The first is when high fidelity data is sparse, and the second one is when the high fidelity data has higher resolution than the low fidelity source. The first case is the most common in the literature. Typically use a few high fidelity data points, for example for wind tunnel testing, combined with CFD simulation to build multi-fidelity surrogate models. Two well-established methods for this type of problem are GAPI-PUD and model based on Gaussian process. For GAPI-PUD applied to multi-fidelity pressure reconstruct, we first perform the SVD or the PUD on the low fidelity database to construct a good PUD basis. Then, using this PUD basis, we try to obtain the coefficient a wiggle that minimize the difference between the actual wind tunnel measurements and the reconstruction of at those specific points. Finally, by multiplying the computed coefficient with the PUD left modes, we can reconstruct the full CP field, as shown in the figure below. The other classic solution to this problem is use models based on Gaussian processes. These regression models are no parametrics, and their main advantage is that they don't just provide a mean prediction but also quantify the uncertainty of that regression. There are different ways to implement this for multi-fidelity, but the most classic approach is the autoregressive model. In this method, we assume that the high fidelity function is equal to the low fidelity Gaussian process scaled by a factor, plus an independent Gaussian process that captures the difference. On the right, we can see the result of this regression on an airfoil. The image shows how including low fidelity data reduces the error, for instance in the suction peak, and also significantly reduce the model's uncertainty compared to using only high fidelity data. Now let's focus on the second scenario. In this case, the high fidelity data not only represents the physics better, but it also has a higher spatial resolution. This case is more relevant from an industrial point of view. The challenge here is that we have many low fidelity simulations because they are cheap, but only a few high fidelity simulations. Our goal is to build a surrogate model that can predict the high fidelity result for unseen flight conditions. To address this problem, we propose a model based on autoencoders, transfer learning, and conformal prediction. In this presentation, I will show you the results applied to the pressure coefficient of the XRF1 aircraft wing. In this case study, the high fidelity data come from RAN simulation with nearly 5,000 nodes. The low fidelity data is a degraded version of this dataset. To do this, we apply PUD and keep only a small number of modes to reduce the fidelity, which smooth the pressure field and reduce the shock intensity. And we also reduce the mesh to 4,000 nodes. Finally, to mimic industrial scarcity, we used a street train test split. Out of the 435 total cases available, we select only 65 cases for high fidelity training and 22 cases for testing. For the low fidelity data, we keep all cases available except the test set to prevent any data linking. Here you can see the autoencoder architecture. Our model is designed to be training in two different phases. In the first phase, we train the autoencoder using only the low fidelity dataset. The idea of this pre-training step is to leverage the large amount of low fidelity data to build a coherent, well-organized latent space based on the wind pressure coefficient. The second step is to transfer the weight of the pre-trained network to a second autoencoder. This network is trained using only the few high-fidelity cases available. For this second phase, we first freeze the encoder to preserve the learned latent space. On the decoder side, we do two different things. First, we fine-tune the original weight. Second, we introduce an additional hidden layer, trained from scratch that scales the dimensionality from the low to the high fidelity. So with the trained model, we fit in with the low fidelity pressure coefficient and get the high fidelity prediction. Since we wanted to retain the native uncertainty estimation that you typically get on Gaussian closure regressions, we decided to implement conformal prediction for our model. The main advantage is that it is distribution free, so the uncertainty are calculated empirically from calibration error without any prior assumptions. Standard conformal prediction provides uniform intervals, but in this case we introduce an adaptive spatial modulation that scales the uncertainty locally. Here we can see the training pipeline of the framework. We begin with the data preprocessing, keeping a strict separation between low and high fidelity data. Then we pre-train the autoencoder using the low fidelity dataset to learn a meaningful latent space and initialize the network weights. Since we only have a few high fidelity samples available, we perform the conformal prediction calibration multiple times, in our case 30 times, using different random chain calibration splits. This allows us to better capture the variability of the design space. Finally, we train the high fidelity autoencoder using all available high fidelity data and stop the training at the average convergence epoch obtained during the calibration. This let us exploit the full dataset while controlling the overfitting. The uncertainty bounds are there obtained aggregating the conformal margins for all our calibration runs. On this slide, we show the regression result for two complex flight conditions. The model accurately reconstructs the pressure field over the entire wind, correctly captures the shock wave in the respective location. Looking at the test metrics, we obtain a root mean square error of 0.084 and a R square of more than 96%, showing a strong predictive accuracy even in this very low data regime. On this graph, we show the uncertainty bounds provided by our conformal prediction framework across different sections of the wind. We can see that the model reconstructs the high fidelity data accurately, and also even in regions where the prediction does not perfectly overlap with the true data, the discrepancies are still well captured within the uncertainty bounds. At the same time, the uncertainty remains narrow and does not become overly conservative. This is also reflected in our coverage results, where more than 95% of the CP values from the test dataset fall within the predicted uncertainty intervals. To conclude, a more detailed analysis of this framework is available in our preprint on arXiv, which you can access via this QR code. The manuscript is also currently under review in the AIAA journal, And in addition, these findings will be presented in this upcoming July at the ECOMAS 2026 conference in Munich. This concludes my presentation. Thank you very much for your attention.